So, hi everybody, my name is Morales. My major is chemical engineering. So, as Wendy said, I'm coming from Oxnard Ventura College. My mentor is Daniel Pinacho, and my professor advisor is Dr. Pancho. And today I'm going to talk about preparing silicon surfaces for 3-5 epitaxy. So, this research is important because nowadays, all of us have cell phones, and these cell phones contain internet. Because we are using a lot of data, we are increasing the data traffic, and we need to find a better way to transfer data from one server to another. Back in the day, they used all electrical wires for long and short distance communications, but with the invention of the optical wires, we switch for long distance to optical wires, and for short distance, sometimes we use optical wires. But we are still using electrical wires for chips because it's to handle and it's more efficient in short distances. So we have the silicon that is a well understood element for the industry, and it's not expensive, but it's not a good light emitter. And on the other hand, we have 3-5 materials, which are basically the elements in the group 3 and the group 5, like boron nitride, aluminum phosphide are examples of these 3-5 elements. So, and these 3-5 elements are mainly used to emit light because and produce lasers. Lasers are used to transfer data with the optical wires. And so our main goal is find a way that we can combine these two great technologies that we have and make a device where we can produce 3-5 materials on top of the silicon, and we're gonna use it to mainly bring this technology to chips, so we can handle all the data in basically chips. So, and using all the photonics in chips. So, but it's not easy just to grow 3-5 material on top of silicon because silicon wafers have some impurities on the top and organic components. So these organic impurities are basically the native oxide, and it's not easy to grow because we have the silicon and the 3-5 crystals that are not the same. So they have some symmetry mismatch that when we grow 3-5 material, it's going to have some defects. So we want to clean the impurities of the surfaces. We're going to actually selectively clean the surface where we want to grow the 3-5 material. If we don't clean the surface, what's going to happen is we're going to have a lot of defects on this 3-5 crystal. But if we have the surface clean and we have all the bonds of the silicon available for the 3-5 material, we're going to have less defects. We have some defects because of the symmetry of the two crystals, but it's going to be better. So the main procedure for us is going to be cleaning the surfaces in order to grow the 3-5 epitaxy. So we're going to have this wafer, it's going to be as received right here. So this is a native oxide. It's going to have some native oxide. This native oxide is coming from the air. The oxide in the air. And also we have some more organic impurities on top of the surfaces. And we have two ways to clean this wafer. If we use solvent, we're going to remove only the organic impurities on the surface of the silicon. And then we're going to introduce our sample to the ultra-high vacuum. And we use the acid and solvent, we actually going to physically remove part of the substrate, like the native oxide and organic impurities. And then we're going to introduce it to the ultra-high vacuum system. And this ultra-high vacuum system is a seal system that is not air in there. So it's going to be available to remove all the contamination. Is not going to be one more time effective. So in the ultra-high vacuum system, we're going to anneal, which is going to skin the sample in order to remove the oxygen and carbon, which is all contamination. So in order to make sure that our sample is clean, we are using XPS. It's X-ray for emission spectroscopy, which is also in the ultra-high vacuum system. So this is basically read the surface of the sample, and it's gonna tell the elemental composition of the substrate. And how it works is very easy. So this X-ray is gonna send some energy to this sample. When the energy of the X-ray hits the atoms of the sample, the different levels of energy of these 2p, 2s, and 2s have different binding energy. So when the electrons are so excited, they're gonna leave. When they leave, they're gonna pass through this electron analyzer or electric chamber. What it does is read the velocity of the electron. Having the velocity of the electron, we can calculate the kinetic energy. With the kinetic energy, we can subtract this amount to the total energy given by the X-ray, and we're gonna have the binding energy. With the binding energy, we're gonna have this spectrum. And this spectrum, because every single element has its own binding energy at different energy levels, so we can know where are the total impurities or the total elements that we have in the sample. So the XPS spectrum looks like this. So this is a graph with binding energy in the X and the Y, the intensity, counts per second. Counts per second is telling us how much of the sample is on the substrate. So in this case, we're gonna have silicon. We know that because it's a silicon wafer, but we have the carbon and the oxygen, which are our impurities in the sample. So after anneal, we know that we almost get all. We actually take out all the oxygen. In this case, what we're looking at is at the peaks that gives the spectrum. But for carbon, we're not able to remove all the carbon in this example. This is just to let you know how we read this, the XPS. So for us, the most important thing is the area integrated in the curve. So this means that the area is how much of the sample we have in the substrate, or how much element we have in the substrate. So for these three substrates that we did, the ultra-high vacuum procedure was constant for everything was of the calcium and anneal. But before we put the substrate into the ultra-high vacuum system, we clean the substrate 1 with only solvents, and then substrate 2 with acid solvents for resist, and substrate 3 with solvent and acid. So our results gives that substrate number 1 with only solvent has a lot of oxygen but remove everything. And for carbon, the same thing, has just a little bit but remove everything. And for the others, we still have some of the contamination. So substrate 1 was our winner, so we have to know how is the surfaces, because also it's important for us how the surface is rough, is soft, or because it's gonna affect the 3 factors. So we took it to the atomic force microscope, which gives a topographic image of the surface. So in this case, we have this line that represents the graph, which is the surface, how it looks like. So this, as we see, like these big gaps and dips and holes are right here. So for this sample, this if we grow 3-5 epitaxy on top of these surfaces, it's going to have a lot of defects on the crystal because of the size. We remove all the contamination, but we have our rough surfaces, which is not good for us. So, and also, we think that these white spots are silicon carbide. Instead of removing all the carbon when it was hot, the silicon was hot, so the carbon was reacting with the silicon, and we have some silicon carbide. That's what we think. So because we know that substrate 1 remove everything, or we think they remove everything, so we said, okay, but maybe if we lower the anneal, or which is the heating, at to 950 instead of 1200, maybe we can remove everything, and we're gonna have a nice surface. But what we got is like almost the same roughness with some dips on it, which is just a little bit better. But in this case, we have these big holes that are not good for our procedure or for what we want. So maybe next time we can add something else to this. So for future plans, we want to clean now, not use solvent. We want to clean with ozone or substrate before we load it to the ultra-high vacuum system. And then we want to find the temperature of the anneal on the surfaces, and we're going to repeat this cleaning procedure to the same substrate in order to remove completely the carbon. And I want to say thank you to all the Palmstrom group, and Dr. Chris, and my mentor, Dr. Nacho, especially because without him I would not be here. I know kind of the stuff because of him. And I want to thanks to Photonics and everybody, Wendy, Jen, and thank you.